Now on to the issue of variables and measurement. So scores are obtained by observing and measuring variables that we use to help define and explain external behaviors. In many instances, the matter of measuring variables is pretty straightforward. So if we want to measure height, for instance, in this country we use inches and feet. Pretty much everywhere else in the world uses meters and centimeters. Weight, eye color, these are other things that are relatively easy to measure because the way that we measure them is pretty straightforward and pretty uniformly agreed upon, and we know when we see them. However, not all variables are this straightforward. A lot of variables are much harder to measure than height, weight, and eye color. We call those constructs. So things like depression, happiness, intelligence. How do I know when I have effectively measured your depression or your intelligence? These are internal attributes or characteristics that we cannot directly observe, but we need to understand them and we need to be able to measure them for explaining behavior. So the way that this is done is using an operational definition. It's a set of measurements that we agree upon for external observable behaviors that we're going to use to define and measure a hypothetical construct. So for example, one really easy way of measuring happiness is with the number of smiles that a person makes in the day. It turns out unhappy people don't smile. So we can simply observe the number of times a person smiles and have some measurement of their happiness. Of course, the number of smiles isn't their happiness, it just represents it, either perfectly or imperfectly, but it's a reasonable way of operationally defining the internal construct of happiness. Same thing with IQ. Some of you may have taken IQ tests and you got a score, 110. Congratulations, you're above average. Well, does the number 110 actually represent your IQ? Is that your IQ? It's really not your intelligence. It's just a measure of it. It's an external measure that we can get so that we can define those things that are much harder to observe. You should also be aware of the difference between discrete and continuous variables. So discrete variables have separate, indivisible categories, and no values can exist between them. So for example, if you roll a single die, it will either show 5 dots on the top or 6 dots on the top. It will never show 4.5. A family either has 2 children or 3 children. We pretty much never talk about having 2.5 children. You either have 6 rooms in your house or 7, but those are sort of discrete variables that cannot be measured in any other way. On the other hand, there are continuous variables which have an infinite number of possible values between any 2 observed values. So take time, height, weight, all of these are continuous variables. I can measure time in hours, but I could also measure it more precisely. I could measure it in minutes, or I could measure it more precisely still in terms of seconds or milliseconds or nanoseconds. A continuous variable is one in which infinitely more precise measurements can be used depending on how precise you want to be. So in any instance in which rounding could occur, then you know you've got a continuous variable. So here's a little graphic depicting continuous measurement. You can see on the first number line that it might be that we call a person weighing 150 pounds someone who weighed anything between, say, 149.5 to 150.5 pounds. Anywhere in that interval, we may actually label the weight 150 pounds. So in reality, there's a pound difference potentially between all of the people whom we are labeling as 150 pounds. It could be somebody weighs 149.6 pounds. It could be somebody else weighs 150.3 pounds. There is in fact a difference between their weight, but anywhere in that interval, we may just label the weight 150 pounds. Those intervals that I'm talking about, from 149.5 to 150.5 pounds, are called real limits. Real limits are displayed on the second number line on the bottom part of the slide. There's going to be a lot more that comes out of this, but for now, all you need to know is that continuous measurements require real limits, which are the intervals around which we define a particular measurement. So we know that every individual that we call 150 pounds doesn't weigh exactly, precisely 150 pounds. So here it is in words. Real limits are the boundaries of each interval representing scores measured on a continuous variable or on a continuous number line. So we know that they're in fact an interval. The real limit separates two adjacent scores exactly halfway between the two scores. There's an upper real limit that marks the top of the interval. So in the example we just talked about, it was 150.5, and a lower real limit that marks the bottom of the interval. So in the example from the last slide, that would be 149.5. At this point, that's all you need to know about real limits. More to come in later chapters, I promise. The most important thing for you guys to know about scales of measurement is that scales of measurement need to be appropriate for answering the question that you want answered and for generating the type of data that you need to do the statistics to answer those questions. So, in other words, it's very important that we choose a scale of measurement which is going to allow us to do the type of statistics that we need to generate an answer to our research question. We could measure height in terms of tall, medium, or short, and that would be really cheap or easy. I could go stand outside, and in not very much time, I could code a whole bunch of people as either tall, medium, or short. But that scale of measurement is really cheap and easy, and anything that is that cheap and easy doesn't give us a lot of power. It's not really that good. It's not that useful in terms of inferences. So what's the average of my tall, medium, or short data set? You can't calculate an average. You can just describe how many people go in each one of those categories. If you want more inferential potential, you would have had to have used a more sophisticated scale of measurement, maybe inches or feet. It's going to take me a lot longer to get the height information on the inches and feet scale of measurement, but then again, once I'm done, I'm going to be able to do a lot more with it. This is a great little chart I included for you guys to understand scales of measurement. So you see all the scales are listed there: nominal, ordinal, interval, and ratio, characteristics of each, and examples of each. It so happens that the scales of measurement are listed from the least complicated to the most complicated. Now, it's safe to assume that the least complicated scale of measurement is going to give you the least amount of inferential potential. That is, the least amount of information that can be learned and the least amount of questions that can be answered. And the most complicated one, on down at the bottom, is going to give you the most information and the most types of questions that can be answered. So let's talk through each one. Nominal scales just label and categorize. There's no qualitative distinctions between them. So examples might be men and women. There's no mathematical difference. There's no numerical difference between men and women. There's no qualitative difference. They're just different. So it labels and categorizes. You might also think Republican and Democrat, or like a diagnosis, cancer, no cancer. There's not necessarily a qualitative distinction, it just defines different groups of things. Next is the ordinal scale of measurement, which also categorizes observations, but it does put them in order by size or magnitude. So think ranking class or clothing size, for example, small, medium, or large. We all know that a medium is bigger than a small and smaller than a large. But how much is the size difference between a small and a medium? Who knows? Nobody knows. So it does put them in order by size or magnitude, but it doesn't define anything about the differences between the groups other than the order they go in. Take Olympic medals as another example. Everyone knows gold is the best, and then silver, and then bronze. but the point difference between the person who gets gold and silver may not be the same as the point difference between the person who gets silver and bronze. For that, you'd have to go to the interval scale. So the interval scale does have ordered categories, and it does have an equal size interval between each category point. The thing that's interesting about the interval scale, though, is that it has an arbitrary or an absent 0 point. And here's what I mean by this. There's no real zero on the interval scale. Let's talk about temperature, for example, temperature Fahrenheit. The difference between 50 degrees and 52 degrees is the exact same amount of difference in temperature as it is between 106 and 108. It's 2 degrees either way. So there's the same difference between each interval in the interval scale. What isn't there is a real 0 point. So 0 degrees Fahrenheit is not the coldest possible temperature. We could have negative scores. It's also not the complete absence of temperature. So 0 is just a point on the scale of measurement. It's not a real true 0. To get a real true 0, you have to go on to the ratio scale. So the ratio has all of the requirements of interval, all of the requirements of ordinal, and all of the requirements of nominal, plus an absolute 0 point, a real true 0 point. So in this case, think about number of correct answers. A person could in fact get 0 answers correct on a test, or time left to complete a task. If there's 0 seconds left on the timer, then that does in fact mean an absence of time. Here's another example. A study assesses the optimal size of study groups. The variable size of groups is, sure, the answer is C. It's discrete and ratio. It's discrete because there's either 3 group members or 4, but never 3.5. There can only be a whole number of group members. And ratio because there could in fact be 0 members of the group. True or false? Variables that cannot be measured directly cannot be measured scientifically. What do you think? Sure, that one's false. Me and lots of people like me have made a living for a long time studying variables that cannot be measured directly. That is, those that require an operational variable. Constructs, that is, any internal states, cannot be observed directly, but they can be measured operationally. Okay, last one in this section. Research measurements are made using specific procedures that define constructs. True or false? Good job. That one's true. Operational definitions assure consistent measurement and provide construct definitions.